Now, next is alkenes. Alkenes. All of you know alkenes are unsaturated system containing a multiple bond, double bonded system. This is the characteristics of alkene. There is a carbon-carbon double bond, and the general empirical combination will be CnH2n, and simplest alkene is ethene, CH2CH2, ethene, and these systems are sp2 hybridized in nature, sp2 hybridized, and it is planar in nature. All of you know the ethene molecule and such double bonded system. It is coming carbon, carbon, single bond, and the 4 hydrogen atoms are available like this. It makes a planar system, sp2 hybridized system, and there is a vacant p orbital. The p orbital will undergo a lateral overlapping leading to pi bond. So this remains sigma bond and this remains pi bond. There is carbon-carbon sigma bond and a pi bond. This is the system of alkene. All of you know that. Alkenes can perform structural isomerism, particularly they can give chain isomerism, they can give position isomerism. When the position of the double bond changes, 1 butane, 2 butane, it can show position isomerism, right? They are able to show stereo isomerism. They are able to perform geometrical isomerism. That is something special in alkenes. Alkenes are able to perform geometrical isomerism. Geometrical isomerism. If you take 2 butane, for example, the typical example, CH3, CH, double bond CH, CH3. It is able to perform geometrical isomerism. There are 2 types of 2-butane. We call it as cis and trans, known to all, cis and trans. And the system will be, if you take a planar system where you have carbon-carbon double bond, where there is methyl group here and hydrogen here, again hydrogen here and methyl group here. So 2 methyl group coming on same side. This configuration we call it as cis configuration. Meanwhile, you can have the next stereo configuration. There is carbon-carbon double bond, and the arrangement comes in such a way, one CH3 group here and the other CH3 group here, hydrogen, hydrogen here. That is trans configuration. Cis trans isomerism. Cis means close to, trans means far apart. So a molecule like 2-butene is able to perform cis trans isomerism. We call it as geometrical isomerism. It is given by restricted rotation across a carbon-carbon double bond. It is also performed in cyclic systems, about which we can discuss on in other classes when we discuss few questions concerned to cyclic systems. Anyway, across carbon-carbon double bond, there can be geometrical isomerism where the 2 groups coming on same side is called a cis configuration, and the opposite side like this is called a trans configuration, right? For this, we need to have 2 different groups. That is the important point. On the concerned double bonded carbon, we should have a group like A and B, like this. So it is AB, AB. 2 different groups coming, you can perform geometrical isomerism. At least in one carbon, same atom or group coming, you don't get geometrical isomerism. For example, propene. Propene cannot show geometrical isomerism. Propene cannot perform geometrical isomerism. What is the issue with the propene? CH3, CH double bond CH2. The point is, this is the geometry center where you can find this carbon contains same atom or groups. So you can't get a two different configuration. C, hydrogen, hydrogen, CH3 and hydrogen. This part of the carbon atom, it is eligible to perform geometrical difference. While these are two same atoms, it cannot give you a geometrical different configuration. So cis-trans isomerism, you will not be able to get, provided a carbon concerned with the double bond containing same atom or group. If it is coming same atom or group, there is no geometrical isomerism. Make it very clear. Rather than where we get geometrical isomerism, it is better to discuss where you don't get a geometrical isomerism. Very simple. If you have carbon-carbon double bond, either of the carbon, if it is XX, there is no geometrical isomerism. Same atom or group coming, there is no geometrical isomerism. Otherwise, you can get geometrical isomerism. A typical example is but2ene gives geometrical isomerism, of which is more stable? Is cis-but2ene more stable or trans-but2ene more stable? But2ene, there are two molecules, cis and trans. They are distinctly isolatable molecules. They are obtained by restricted rotation across carbon-carbon double bond. Which one is more stable, cis or trans? All of you know, trans is more stable than cis as there is lower steric hindrance. The steric hindrance is low. The steric repulsion is low. Steric hindrance is low. So trans configuration is more stable than cis configuration. Quite naturally, when the stability increases, heat of hydrogenation decreases. Heat of hydrogenation is lower for trans than cis. Which got a greater boiling point? Which got a greater boiling point? All of you know, cis having a greater boiling point. Why cis is having a greater boiling point? Cis is having a distinct dipole moment. The dipole moment for cis is greater. You have CH3 and CH3 like this. There is a polarity in this direction. There is a polarity in this direction. There is a net polarity in this direction. It has got a distinct dipole moment. When the dipole moment exists, molecular attraction increases. Molecular attraction increases, boiling point increases. So cis configuration having greater boiling point than trans. What is the problem with the trans? For trans, the dipole moment is found to be 0. Why for trans the dipole moment is 0? Very, very simple. You have carbon-carbon double bond across which you find methyl group is here and the next methyl group is here. Opposite position. So what? A dipole moment in this direction is mutually cancelled in this direction. They are mutually cancelled and the net dipole moment is equal to 0. Therefore, it is non-polar in nature. Therefore, molecular attraction decreases, boiling point decreases. So, boiling point is greater for cis, less for trans. Stability more for trans, less for cis. Heat of hydrogenation lower for trans, higher for cis. Melting point higher for trans because trans is having a molecular symmetry. This is trans while this is cis. When you compare cis and trans, trans is having a molecular symmetry and molecules can be closely packed. Therefore, due to close packed arrangement, melting point is greater in trans compared to cis. Rather, cis is more loosely packed in the solid state. So, you need to review various geometrical isomerism and its consequences, compare with the various type of alkenes as much as possible. Right? Try to figure out how do you give the IUPAC name, including the cis-trans configuration. Suppose I am giving you a molecule. You please try to figure it out. Suppose I am giving you such a molecule. I am giving you this molecule. Can you find out the IUPAC name of this molecule, including cis-trans configuration? All of you know it is 1, 2, 3, 4, 5, 6, 7 carbon atom. 7 carbon atom, two double bond. It is called heptadiene. It is called heptadiene. So it is 1, 2, 3, 4, 5, 6, 7. So it is hepta 2, 4 diene. I want to know what is the configuration at a 2 and 4. Is it cis or trans? At a 2 position, is it cis or trans? At a 4 position, is it cis or trans? You can try how to give the complete IUPAC name of the molecule, including stereo configuration. I am leaving to you. You please figure out. Of course, we are going to discuss this matter in the course of study, in the class. Of course, there will be questions concerned. During the discussion of the questions, we are going to discuss even more on this. Right? That is about the features of alkene molecules. Now let's have a talk on preparation of alkenes. Preparation of alkenes. Number 1, from alkynes. Number 1, from alkynes. Alkynes can be partially reduced to get alkenes. Alkynes can be partially reduced to get alkenes. Alkynes can be converted to alkenes by partial reduction. If you take ethyne, when treated with palladized charcoal, it is called Lindlar's catalyst. All of you know Lindlar's catalyst. Palladized charcoal or palladium with barium sulfate poisoned with sulfur or quinoline called Lindlar's catalyst, which we are trying to suppress the catalytic activity of palladium by adding some poisonous substances. We are trying to reduce the active centers of palladium. Thereby, we are trying to give partial reduction. Triple bond is reduced to double bond on adding a calculated amount of hydrogen, not excess hydrogen. So, calculated amount of hydrogen added with a controlled catalytic action using palladized charcoal, we get triple bond. Added with a limited amount of hydrogen, you get ethyne converted to ethene. This is catalytic hydrogenation, where alkyne converted to alkene. Right? There is something special to be noted in this reaction. Suppose we are taking an alkyne which is of this category. Suppose we take an alkyne of this category, that is RC triple bond Cr. Please understand, when this is treated with the palladized charcoal, that is Lindlar's catalyst, with the calculated amount of hydrogen, you will get alkene which is cis configuration. You will get alkene with a cis configuration. A catalytic hydrogenation, partial reduction of alkyne, which is possible to give an alkene containing cis-trans isomerism. Palladized charcoal reacting with the calculated amount of hydrogen when alkyne partially reduced to alkene, where the alkene is subjected to perform cis-trans isomerism, the product obtained is cis. Meanwhile, the same alkene treated for a controlled reduction using sodium in liquid ammonia. Suppose it is treated with the sodium in liquid ammonia, what the product you are going to get is a trans product. You will get a trans product. This is something special you need to make a note on to. An alkyne treated with the Lindlar's catalyst, an alkane which is possible to give you an alkene containing cis-trans isomerism. If you treat with the Lindlar's catalyst, you will get cis configuration. If you treat with the sodium ammonia, you get a trans configuration. And this reaction sometimes also called a Birch reduction. So during Birch reduction, you get a trans configuration. Using reduction using Lindlar's catalyst, you get a cis configuration. A very important reaction concerned to preparation of alkene from alkynes. Okay. Next one. Next reaction from alkyl halides. Alkyl halides treated with alcoholic KOH. You can get alkene. Alkyl halides treated with alcoholic KOH. You can get alkene. If this is treated with an alcoholic solution of KOH, there will be dehydrohalogenation leading to the formation of an alkene. Ethyl bromide will produce ethene. Ethyl bromide will produce ethene. Try to understand how the reaction is taking place. There is CH3 and there is CH2Br. When treated with an alcoholic solution of potassium hydroxide, try to understand clearly. This halogen is leaving along with the K plus. It is out as KBr. Now this OH minus will abstract a proton from beta carbon. This is alpha carbon from which halogen is eliminated, and this is beta carbon from which hydrogen is eliminated along with OH minus, and this double bond will be shifted between carbon and carbon, and the net result will be you get ethene. You get CH2 double bond CH2 double bond CH2, you get ethene. I repeat, halogen gone along with the K plus, KBr out, and OH minus attacks on beta hydrogen. That's why it is called a beta elimination reaction. Beta elimination reaction. A hydrogen is eliminated from beta carbon. It is called a beta elimination reaction, and you find a double bond is created between carbon. This is called dehydrohalogenation, preparation of alkene from alkyl halide. Okay. There is another procedure, that is dehalogenation reaction. Imagine you have CH2Cl, CH2Cl. This is vicinal dichloride. This is vicinal dichloride. All of you know 1,2-dichloroethane. It is called vicinal. Vicinal means two chlorine atom coming on adjacent carbon atom is called vicinal. If it comes on same carbon atom, all of you know it is called geminal. Gem dichloride, vis dichloride. This is a vis dichloride. The two chlorine atom coming on neighboring carbon atom. Suppose you have such a vis compound, vis dichloride. Imagine this is treated with zinc. There will be dehalogenation. What will happen is zinc will take away. Just try to assume the net result of the reaction in such a way. Zinc is carrying the two chlorine out as zinc chloride. What will remain is a double bond comes between the two carbon atom, and the net result to figure out to be CH2 double bond CH2. You get ethene. So vicinal dichloride is converted to ethene. Dehalogenation reaction. This is dehalogenation reaction. What was the previous one? That is a dehydrohalogenation. This is dehydrohalogenation. This is dehydrohalogenation. A hydrogen and halogen is expelled. While the one which we have seen now, it is dehalogenation reaction. And finally, in the preparation of alkene, dehydration process. Dehydration process. An alcohol heated with a concentrated sulfuric acid. Suppose I am taking ethyl alcohol, for example, ethanol. Ethanol heated with a concentrated sulfuric acid to a temperature 443 Kelvin. Temperature is important. Temperature is important. Reagent is important. You are doing dehydration process. It is called a dehydration process. All of you understand what is meant by dehydration? Means removal of water. What is being removed? This OH along with a hydrogen here removed as water, and the net result will be you get a double bond here. It is CH2 double bond CH2. Ethanol is converted to ethene. Ethanol is dehydrated to ethene. That is the preparation. That is also elimination reaction. All the three reactions commented now, dehydrohalogenation, dehalogenation, dehydration, they are elimination reaction. Let me tell you the details of this reaction. How the details of this reaction can be understood. Very simple, very simple. You see that CH3, CH2, OH. First of all, it is getting protonated. The OH oxygen is getting protonated. You get CH3, CH2, OH2 plus. Once it is converted to OH2 plus, protonated alcohol, immediately water molecule will be out. This is out as water molecule. Now this will turn a carbocation. You get a carbocation. This is a carbocation you are getting. And now from this carbocation, there is a deprotonation reaction. It undergo deprotonation reaction. This hydrogen will be removed as H plus and this electron pair will be switched between the two carbon atom, leading to the formation of alkene, that is ethene. So it is a two-step mechanism, protonation, three-step mechanism, protonation, dehydration, deprotonation. Protonation step 1, dehydration step 2, deprotonation step 3 to get final alcohol. Temperature is very important. For example, heating with the concentrated sulfuric acid, or you can use any dehydrating agent including alumina or something like that, or any protic acid is enough, no problem. But specific high temperature is required because at different temperatures, different products are obtained. For example, heating with sulfuric acid at a temperature of 413 Kelvin, you will get ethers like that. So 443 Kelvin, close to 450 Kelvin essentially required for getting ethene from ethyl alcohol, right? That is the preparation of alkene. Product preparation number 1, partial reduction of alkynes, where two reactions we have seen using palladium Lindlar's catalyst and sodium in ammonia. Lindlar's catalyst gives this product, sodium in ammonia give trans product, right? And dehydrohalogenation, dehalogenation, dehydration. Is it clear? Preparation of alkenes. Next, chemical properties of alkene. Chemical reactions of alkene. We are going to see some important chemical reactions of alkene. Alkenes having loosely held pi electron, easily attacked by an electrophile, and it gives electrophilic reactions. And let's see some of the reaction. Addition of dihydrogen, already we have learned. Addition of dihydrogen. Alkenes upon adding with hydrogen, CH2, double bond CH2, added with hydrogen using catalyst, nickel, platinum, palladium, etc. Upon heating, hydrogen will be added over the double bond and you get CH3, single bond CH3. Catalytic hydrogenation, the given alkene correspondingly converted to alkane. Ethene becomes ethane, propene becomes propane, already discussed. Second one is halogenation reaction. Halogenation reaction. Regarding halogenation, we can see bromination. CH2 double bond CH2 added with the bromine in presence of CCl4. It can be considered as a test for unsaturation. Bromine will be added across the double bond. You get vicinal dibromide. One bromine will be added here and one bromine will be added here. You get vicinal dibromide. CH2Br, CH2Br. You get vicinal dibromide. And this can be used as a test for unsaturation because as a result of this reaction, the orange-red color, orange-red nature of Br2 getting decolorized. It's a test for unsaturation. Number 1. Number 2, the reaction has got a speciality. It is giving anti-addition. when you look at the mechanism involved in the reaction, this is ethene, CC double bond. And this CC double bond polarizes Br2, which is polarizing as delta plus and delta minus. And this electron, pi electron, is attacking on bromine. Meanwhile, this bond will be broken. And thereby, you are going to get a cyclic bromonium ion. This bond starts breaking and it starts forming a cyclic bromonium ion. This is the intermediate you are getting. And the broken Br minus will be attacking from the opposite side. So one bromine is added from the bottom of the plane, while the next bromine added from top of the plane, and is called the anti-addition. This is called the anti-addition. So bromination is anti-addition, number one. Number two, it can be used as a test for unsaturation. The orange-red color will be decolorized. So hydrogenation reaction. Number two, halogenation reaction. Addition of halogen. That is a electrophilic addition reaction. Next is addition of hydrogen halide. Addition of hydrogen halide. That too is a electrophilic addition reaction. If you take a symmetric alkene like ethene, ethene is a symmetric alkene and is added with say HBr. So what happens is, first step addition, the H plus will be attacked by the CC double bond. You are getting CH2, sorry, you are getting CH3, CH2 plus. That is first step addition. And now it is attacked by Br minus, that is nucleophilic attachment. You are getting CH3, CH2 Br, and that is hydrohalogenation reaction, addition of hydrogen halide. First attack will be H plus, hence it is electrophilic addition reaction. The slowest step of the reaction involved addition of H plus. Hence it is called electrophilic addition reaction. Okay. Now only one product is obtained if you take a symmetric alkene. Suppose you are taking unsymmetric alkene. Suppose the taken molecule is propene. CH3, CH double bond CH2 added with HBr. You can have two different products. One is hydrogen added here, bromine added here. You get product number one. CH3, CH2, CH2, Br, that is 1-bromopropane. Number two is hydrogen added here and bromine added here. You get CH3, CH, Br, CH3, that is 2-bromopropane. 2-bromopropane, and this will be major product. I'm sure all of you remember the very popular called the Markovnikov addition reaction. Markovnikov addition. The negative part of addendum. This is the positive part and this is the negative part. Negative part of addendum predominantly connected to carbon containing less number of hydrogen atom. The negative part of addendum predominantly connected to carbon containing less number of hydrogen atom. So Br minus will be predominantly connected to CH part, and you are getting this as the major product. That is called a Markovnikov addition. Of course, you must try to understand why and what is the reason for this mechanism you need to learn. Let's see what is the reason for such an addition. See, Markovnikov addition or the normal hydrobromination reaction occurs via carbocation mechanism. Let's have a look at CH3CH double bond CH2 propene, which is unsymmetric alkene, is added with HBr. The first step addition will be addition of H plus. You will get two possibilities. you have two possibilities. Hydrogen may be added to this carbon or added to this carbon. That means you will be getting CH3, CH2, CH2 plus, or you may get CH3, CH plus, CH3. So hydrogen may be added here, you get a carbocation in this carbon, case 1. Hydrogen may be added here, you get a carbocation in the second carbon. This is a primary carbocation, all of you know, and this is a secondary carbocation which is more stable. So naturally a question arises, which path will dominate? No doubt, the second path will be dominating. This path will be dominated because that gives a secondary carbocation which is more stable. Now the last step reaction, bromine is added. Last step reaction, bromine is added. Here as well as here, Br minus will be added over here. Br minus will be added over here. You are getting CH3, CH2, CH2Br 1 bromopropane and CH3, CHBr, CH3, 2 bromopropane, which is obtained as a major product because major path of the reaction happening in the second pathway where you get a more stable secondary carbocation, and this is called a Markovnikov addition, all of you know. So whether you add HCl, HBr, HI or any unsymmetric addendum, the result will be according to Markovnikov rule. Now suppose HBr is added with the propene. Suppose HBr is added with the propene in presence of light or in presence of some peroxides. Then the scenario will be opposite. Imagine CH3, CH double bond CH2 added with HBr in presence of light or in presence of some peroxides. Peroxides are well-known radical initiators. Then the product will be opposite to Markovnikov rule, and the major product will be, of course you get two products, 1 and 2. Major product will be CH3, CH2, CH2Br. 1 bromopropane will be major product while 2 bromopropane will be minor product. And that is called anti-Markovnikov addition. Anti-Markovnikov addition. And that is called a peroxide effect. Anti-Markovnikov addition, peroxide effect, also called a Karash effect. Karash effect, anti-Markovnikov addition, peroxide effect. And remember, that is applicable only to HBr. That is applicable only to HBr. Markovnikov addition applicable to all species. Anti-Markovnikov addition applicable only to HBr. Let us try to understand why. Because we need to learn the mechanism concerned. It is there in the text. You see what is happening in this case. It is nothing but, suppose we are taking a peroxide. Imagine we are taking a peroxide, for example, benzoyl peroxide is taken or acetyl peroxide is taken. C6H5COOOCOC6H5. This is benzoyl peroxide, which is taken as a catalytic agent over here. This is highly prone to go for a homolytic fission. A peroxide is highly known for the homolytic fission, forming free radicals. It will form free radical. You get benzoyl free radical. And this benzoyl free radical will immediately undergo a fission like this, giving the formation of phenyl free radical by expelling carbon dioxide. This part of the molecule will be expelled as carbon dioxide and you get phenyl free radical. And this phenyl free radical interact with the HBr, and now HBr will undergo a free radical fission and you get H dot. H dot interact with the benzene, phenyl, you get benzene, and you are getting bromine free radical, and this is the hero of the show. And now that bromine free radical attacks propene. Propene is attacked by bromine free radical. This is attacked by bromine free radical, and there will be two pathways. First pathway will be like this: CH3, CH2, CH2Br dot. And second pathway could be CH3, CHBr, CH2 dot. See, it is not Br minus, sorry, it is Br dot, bromine free radical. So bromine free radical attacking over this carbon, you get this. Bromine free radical attacking over this carbon, you get this. I'm sure you understand. This is a primary free radical, while this is a secondary free radical. Which is more stable, primary or secondary? Secondary free radical is more stable. Secondary free radical is more stable. So which pathway will dominate? Like I was asking in the previous case, which pathway will be dominating? This pathway will be dominating. This path will dominate than the other one. Right? Now the reaction continues. This is the intermediate which is interacting with another HBr. There will be homolytic fission. You get H dot and Br dot, and that H dot is attacking here. You get the final product CH3, CH2, CH2Br as final product, and major product as this pathway is happening major. And Br dot will continue the reaction. Now again, this is interacting with HBr, undergoing a homolytic fission. H dot will come here, and you get CH3, CHBr, CH3. And Br dot will continue the reaction. This will be only a minor product. This is anti-Markovnikov of addition. So Markovnikov of addition, major product is 2-bromopropane, while anti-Markovnikov of addition, major product will be opposite to the previous case. Because Markovnikov of addition happens with the carbocation mechanism. Here it happens with the free radical mechanism. The entire mechanism has changed. This is called a Karash effect. This is called a peroxide effect. This is called anti-Markovnikov of addition, limited to HBr addition only. Sir, why not HCl? HCl is bond strength is bit more and not comfortable to go for a homolytic cleavage. HCl bond strength is bit more and is not comfortable to give a homolytic fission. That is the problem. Now, what about HI? HI bond strength is weak, and of course it can give you homolytic fission comfortably, and of course you will get I dot, no problem. But the point is, I dot is not interested to attack propene. The way Br dot is attacking propene, I dot is not interested to attack with propene thermodynamically. Rather, the bigger I dot radical is comfortable to interact to I dot will be converted to I2. That is a stable reaction rather than attacking on propene. So such various consequences we find, and anti-Markovnikov addition, Karash effect, peroxide effect is limited to HBr addition only. Very important area from the chapter. I don't have to tell you. Everybody remember Markovnikov addition, anti-Markovnikov addition. Right? That is about a very important reaction of alkene, including mechanism. Next is addition of sulfuric acid. Addition of sulfuric acid. It will be added the same way. Ethene added to sulfuric acid. In the same way, nothing special in it. You see, CH2, double bond CH2 added with sulfuric acid, HSO4, plus and minus. Hydrogen comes here and HSO4 minus comes here. You get CH3, CH2, HSO4. Ethylene hydrogen sulfate is obtained. And if you take a unsymmetric alkene, the addition will be according to Markovnikov rule. Okay. Next it is addition of hydrogen, addition of water, hydration process. Hydration process once again, suppose I am taking propene, CH3, CH double bond CH2, added with water, it is an acid catalyzed reaction. It is an acid catalyzed reaction, H plus and OH minus, where the OH minus comes predominantly. Of course, you get two products, one propanol, two propanol. The product obtained is alcohol. Whether you get one propanol or two propanol predominantly, where the OH minus get connected, first carbon or second carbon. Where the OH minus getting connected, it will be on the second carbon, Markovnikov addition, and hydrogen will be coming here, and the major product obtained will be 2-propanol. CH3, CHOH, CH3 is major product according to Markovnikov rule. Is it clear? Next reaction, very important one, oxidation using cold dilute alkaline KMnO4 called Bayer's reagent. Oxidation using cold dilute alkaline KMnO4. Oxidation using cold dilute alkaline or aqueous KMnO4 solution called Bayer's reagent. Bayer's reagent. And it is basically a hydroxylation reaction. If you take ethene treated with Bayer's reagent, it is basically a hydroxylation reaction. You can find the OH group is added at the vicinal position. One OH will come here and one OH will come here. You get vicinal glycol. Ethylene glycol is the product. Ethylene glycol is the product. Vicinal glycols are obtained. And it is a test for unsaturation. The purple color of KMnO4 will be decolorized. A simple test for unsaturation. Hydroxylation reaction. Unlike bromination, it will be syn addition reaction. It is a syn addition reaction normally. Right? And there is an extended version of oxidation. Suppose you are doing the oxidation with acidified KMnO4. Suppose you are using acidified KMnO4. KMnO4 in acid medium, there will be a drastic oxidation reaction. Imagine you are taking CH3, CH double bond CH, CH3 treated with acidified KMnO4 solution. That is a drastic oxidation where you find the carbon-carbon double bond is broken. The carbon-carbon double bond is broken. If you have a carbon with hydrogen, you will get a carboxylic acid. You get CH3, COOH. This carbon will be converted to carboxylic acid. Quite similarly, this carbon will be converted to carboxylic acid. You get CH3COOH, CH3COOH. You are getting 2 mole CH3COOH. Suppose there is no carbon in it, it will be converted to ketones. It will be converted to ketones. Anyway, there is cleavage of carbon-carbon double bond. Imagine the alkene taken is this one. CH3C, CH3, double bond CH, CH3. When treated with an acidified solution of KMnO4, it will be a bond cleavage over here. This carbon will be converted to COOH and the product obtained is 1 mole this. Meanwhile, this part of the system, this carbon will be converted to ketone. So you get CH3, CO, CH3 and this is converted to CH3, COOH like that. So if the breaking carbon is CH group, you get COOH. If the breaking carbon is C, you get keto group. If the breaking carbon is CH2, it is converted to formic acid, which is easily oxidized to carbon dioxide. That is oxidation reaction, right? And the last important reaction is ozonolysis. Alkene taken for ozonolysis reaction. Alkenes taken for ozonolysis reaction. Ozonolysis reaction. Suppose I am taking ethene. ethene first added with ozone, you will get ethene ozonide. Ozone is added across the double bond and you get a special type of addition product. We call it as ethene ozonide. This is called ethene ozonide. Right? Now this treated with zinc and water. It is treated with zinc and water. There will be a reduction cleavage. It is going to cleave like this. And this oxygen is taken away by zinc. You get zinc oxide. Right? And this part of the system will be converted to respective their product. You see CH2O, CH2O. That means you are going to get 2 mole formaldehyde. You will get 2 mole formaldehyde. Right? And it's very simple to predict the products obtained. Very simple. You see, what you need to do is CH2 double bond CH2. What is the ozonolysis product? Ozone, first treated with ozone, then treated with zinc and water. What will be the product obtained? Very simple. Just cleave the double bond. Just cleave across the double bond. You attach one oxygen on both sides, predict the product. It is CH2O, that is HCHO, formaldehyde, 2 mole. What if we are taking propene? What if we are taking propene CH3, CH double bond CH2? What will be the product? You just cleave over here. One oxygen here, one oxygen here. You are getting CH3CHO, ethanol. 1 mole ethanol, HCHO, 1 mole formaldehyde. So 1 mole ethanol, 1 mole formaldehyde. Ozonolysis is primarily a test for unsaturation. It is a test for the number of unsaturation. It is a test for the type of unsaturation. It is a test for the position of the unsaturation. Very, very important. It can be used for testing unsaturation. It can be used for testing whether it is a double bond or a triple bond. It can be used for testing how many double bond is present. It can be used for testing where the double bonds are. Imagine there are 3 double bonds. In a long chain, there is 3 double bond, or in a cyclic system, there are 3 double bond. Where the double bond is present, you can determine. So the unsaturation, type of unsaturation, number of unsaturation, position of unsaturation can be determined by ozonolysis. Ozonolysis, adding with oxygen, followed by zinc and water, you get reduction cleavage, zinc and hydrogen peroxide, you will get oxidative cleavage giving acid derivatives. Try to keep it in mind. And you know, ozonolysis is one of the important reactions which helped us to see that in the benzene ring, there are 6 carbon atoms which is followed by alternate double bond present. And you can try. I'm giving you a chance. I'm giving you as a challenge and chance also. What will be the ozonolysis reductive cleavage product if you take benzene? Suppose benzene treated with the ozone and water. I'm leaving to you. Benzene treated with ozone first, followed by treating with the zinc and water. What will be the product obtained? This is one of the reaction which helped to identify the structural detail of benzene. And that is one of the most important reaction characteristics of alkene. And finally, there is one reaction commended for alkene which we are discussing in detail in polymers. Polymerization. Alkenes can undergo polymerization, giving variety of polyalkenes. That is also commended there. That's all regarding the characteristics of alkene. So we were talking about preparation and properties of alkene. We had a talk on geometrical isomerism on alkene, various preparation techniques of alkene, and various chemical reactions. What are the important chemical reactions discussed? Addition of hydrogen, addition of halogen, addition of hydrogen halide, Markovnikov addition, anti-Markovnikov addition, addition of water, hydration process, oxidation, Bayer's test, Bayer's reagent, using Bayer's reagent, then oxidation using acidified potassium permanganate, and finally ozonolysis. Okay.